Rohini College of Engineering and Technology from Department of Civil Engineering. So this is our civil engineering subject, 7th semester. Our subject title is CE 8703 Structural Design and Drawing. I am Michael Devadurai, Assistant Professor. So now we can see about the topic is design a interior panel of flat slab. In example 1, so design an interior panel of flat slab floor system for a warehouse 24 meter into 24 meter divided into panels of 6 meter into 6 meter. There's one largest structure, one largest building, so we call it as a warehouse. It will be converted into panels of 6 meter into 6 meter. So we can take in that will be one slab size, one flat slab size. It will be taken as a 6 meter into 6 meter. Then live load is equal to 5 kilonewton per meter square. In column size 400 mm diameter and M20 grade concrete. Then Fe 415 HYST4. So it will be the column size. It will be given in our diameter shape. So we can assume that the circular column shape. So see the diagram. So this is our warehouse. So we can view from the top view of that building. So we can split into 6 meter into 6 meter on panel size. Then this is the flat slab. So column strip, middle strip and column strip. So above the column we call it as a column strip slab. So middle in between the two columns we call it as a middle strip slab. Then thickness of slab at midspan. So dimensions of flat slab. So thickness of slab at midspan. Then span depth to ratio is equal to 26. So this formula is taken from our code book IS 456-2000 page number 37. So our percentage of tension reinforcement 0.4 is assumed. So for tension reinforcement maximum all the formulas we can assume that 0.4 percentage. Then this also taken from our IS 456-2000 page number 38, because the span to depth ratio is equal to 26 into modification factor. So now need to find out the modification factor. So we need that. So modification factor from the Fs equal to 0.58 into Fy. So 0.58 is the constant value. Then Fy is given in our question. So Fy is equal to 415. Then Fs equal to 240.7 Newton per mm square. So one graph will be there in page number 38. So we can easily find out the modification factor. Then modification factor is based on Fs and percentage of tension reinforcement. So span to depth ratio is equal to 26 into modification factor is 1.3 is equal to 33.8. So span to depth is equal to 33.8. Then we know the span length. So span length is 6 meter, because the panel size it will be taken as a span size. So 6 meter converted into mm, so 6000 mm. So depth is equal to 6000 divided by 33.8. So d is equal to 177.5 mm. So we can round it as 170, or it will be take a 180 also you can take. So no problem. Then overall depth capital D is equal to 170 plus 30. 30 means cover slab. So in our flat slab we already told that flat slab it will be taken as cover as a 30 mm. Then overall the capital D is equal to 200 mm. So thickness of slab at a drop. So drop means slab thickness plus 100. That 100 will be assumed. We can take it as a drop thickness is assumed as 100. So thickness of slab at a drop portions. So drop portions where the thickness is what? Because 200 plus 100 is equal to 300 mm. Then column head diameter. We know that column head diameter is below the drop panel. So we can the one constant formula 0.25 into L. So L means span length. So 0.25 into 6 is equal to 1.5 meter. Then length of drop is equal to L by 3. So L we can know that 6 by 3 is equal to 2. Then drop width is equal to column head diameter into length of the drop. We can take as the drop width. So 1.5 into 2 meter is equal to 3 meter. So you can easily assume this drop width is equal to column strip. So basically we can assume that because all the sides are the equal sides, so width of the middle strip also equal to drop width. Then step number 2, find load. So live load is equal to given in our question, so that will be taken as 5 kilonewton per meter square. Then dead load is equal to 0.5. This is the condition for the finding on the dead load, because 1 by 2, half of the distance will be taken and into unit weight of concrete. So half of the means 1 by 2 is equal to 0.5. Then 0.3 is the thickness of slab at the drop portion. Then 0.2 is the thickness of slab at the middle strip portion. Okay, into unit weight of concrete, we know that 25 kilonewton per meter cube. So finally the dead load is equal to 6.25 kilonewton per meter square. Then floor finish is equal to 0.75. So sometimes floor finish in given in our question, otherwise they will not given, you can assume that 0.75 to 1 up to 1 kilonewton per meter, so you can take in that floor finish. Then total load is equal to add the all loads, so live load plus dead load plus floor finish is equal to 12 kilonewton per meter square. Then factor load, it is simply multiplied by using the factor load. The factor load is 1.5, this is a constant. So 12 into 1.5 is equal to 18 kilonewton per meter square. The factor load means just a safety for our building. Step number 3, find bending moment. So this formula is taken from our code book IS 456-2000, page number 55. Then total moment M is equal to W into Ln divided by 8. So this formula is in our code book, page number 55. So now we can find out the Ln. Ln means clear span. So our span length is 6 meter. So now we can find out the clear span length. So reduce the column head diameter. So 6 minus 1.5. 1.5 is our column head diameter. So that will be taken as minus as a clear slab. So 6 minus 1.5 is equal to 4.5 meter. Then W is equal to WU into L2 into Ln. So this formula also code in our code book. So WU is, we can already find it in step number 2. Then Ln is equal to 6 meter. Then L is equal to 4.5 meter. So W is equal to 486 kilonewton. So total moment. So total moment is equal to WL by 8. We know that formula. So apply the values. We got the answer is, our answer is 274 kilonewton meter. So column strip moments, we've taken it 70%. So column strip movement is divided into one negative movement and another one is positive movement. So negative total column strip is 70%. So that will be separated into negative movement for 49% and positive movement for remaining 21%. Total 70% for column strip. So 49% of total movement. So 49 divided by 100 into 274 is equal to 134 kilonewton meter. Then 21% of total moment, 21 by 100 into 274 is equal to 58 kilonewton meter. Then again middle strip moment. So middle strip moment remaining 30%. So column strip already we taken as 70%. So middle strip taken as a remaining 30%. The negative bending moment is equal to 15% for negative bending moment and 15% for positive bending moment. So 15% for negative bending moment into total bending moment. So 15 by 100 into 274, that is equal to 41 kilonewton meter. Then positive bending moment also say as well as 15% into total moment. Step number 4, check for thickness of slab. Then we know that formula D is equal to root of mu by 0.138 FCK into B. So mu is in our previous step we can find at the moment, it will be taken as the maximum moment. Okay. So thickness of slab near drop based on column strip. So take the maximum moment for column strip is equal to 134 into 10 power 6 is our maximum moment, and divided by 0.138 is a constant value. Then FCK is given in our question. So B is equal to, we can assume this. So in this problem we didn't assume that B is equal to 1 meter, because they will be given as here, we can take as the middle strip width of the middle strip is equal to 3 meter. So we can apply in this step in mm. So we need to convert the 3 meter to mm. So 3000 mm. So D is equal to 127 mm. The thickness of slab middle strip. So our middle strip maximum moment is 41 kilonewton meter. So 41 into 10 power 6 divided by 0.138 into 20 into 3000 mm. So D is equal to 70 mm. So thickness of slab near drop for column strip. we find out the overall depth. So overall depth of drop is equal to capital D is equal to 300 mm. So small d is equal to 300 minus 30 is equal to 270 mm, or 30 is the cover slab. So thickness of slab for middle strip, overall depth is equal to capital D is equal to 200 mm. Then effective depth D is equal to 200 mm minus 30. 30 is the cover slab. So small d is equal to 170 mm. Then step number 5, check for shear stress. So total load on circular area, W is equal to 4 by 5 by 4 into D plus D the whole square. So D means, capital D means column head diameter, and small d means effective depth. The W is equal to total load. So apply all the values. You got the W is equal to 44.3 kilonewton. The next shear force is equal to total load minus load on circular area. So this is our formula for finding out the shear force. So total load is the load into span sizes, W into L into L. So this is our finding of the total load method. So total load is equal to 18. So span length is 6 meter into 6 meter. Then total load on circular is equal to 44.3. We can find it in our previous step. So shear force is equal to 603.7 kilonewton. So shear force per meter of perimeter. So in this step we need to find out the shear force up to per meter. So per meter means based on column head diameter and effective depth. So 603.7 divided by capital D plus small d. So capital D value is 1.5 meter. 1.5 means column heads diameter, and capital D is small d is equal to effective depth. So 270 mm. So in this step we can apply in the meter. So 0.27 meter. So shear force per meter of perimeter is equal to 340.66 kilonewton. So shear stress tau V is equal to shear force by BD, because load by area, or load is taken as a shear force, BD is my area. So we know that shear force that 341.07 into 10 power 3, then B is equal to 3000 mm, and D is equal to our effective depth is 270 mm. So shear stress tau V is equal to 0.42 Newton per mm square. Then permissible shear stress is equal to Ks into tau C. So Ks in our code book page number 58 and 59 from IS 456 2000. So see that code book page number 58 and 59. The Ks formula is there. So K is equal to 0.5 plus beta C. So beta C is the unknown value. So we need to find out the beta C. So beta C is equal to L1 by L2. So beta C is equal to L1 by L2 is our span length. L1 means span length 6 meter into 6 meter. So 6 by 6 is equal to 1. So K is above, K is equal to 0.5 plus beta value is 1. So apply that. So find K is equal to 1.5. But K is not more than 1 meter. So K is equal to 1. It will be taken as a 1. So tau C is equal to 0.25 into root of FCK. So FCK is given in our question 20 Newton per mm square. So tau C is equal to 1.118 Newton per mm square. Then permissible shear stress Ks into tau C. This is the formula. So Ks is a 1 and tau C is a 1.18. Already we find it. So permissible shear stress is equal to 1.18 Newton per mm square. So it will be greater than shear stress. So permissible is greater than shear stress, hence safe. So step number 6, find reinforcement for column strip. First one is negative moment. So reinforcement, we need to find out the column strip separately for column strip and middle strip. So in our column strip for negative moment for separate and positive moment also separate. So middle strip also negative moment also separate and positive moment also separate. We need to find that. Then mu is equal to 0.87 Fy AST into D, 1 minus AST Fy divided by BD into FCK. So this formula is finding out, used to find out the AST value. So this formula is in our code book page number IS, page number 96, IS 436 2000. So for column strip finding out AST, it will be taken as the column strip maximum moment. So our column strip maximum moment is 134 kilonewton meter. So 134 into 10 power 6 is equal to 0.87 is a constant value, and FO is the given in our question, Fe 415. It will be taken as 415 Newton per mm square. Then AST is the constant, because in this step we need to find out the AST value. So D is equal to effective depth. So effective depth is D is equal to 270 mm. So 1 minus AST into 415, then divided by BD into FCK. B is equal to 3000 mm and D is equal to 270 mm and FCK is equal to 20 Newton per mm square. So finally we got one equation mode form. So using calculator to finding out the AST value. So from A is equal to 2.49, then B is equal to 97.48 into 10 power 3 and C is equal to 134 point into 10 power 6. So you will calculate in go to using calculator, go to mode portion and equation portion and degree portion, you take as a second order degree. Sometimes it will be given in our equation form as a third order, you will be click the third order degree. So in this step we can enough for second order, so we will be taken as a second order degree. So x1 and x2 value given you got in our calculator's answers, then it will be taken as least value for AST. So AST's least value is 1426 mm square. So finding out AST for per meter, okay, per meter. So our column strip width is the 3 meter. So finding out for per meter, so AST for per meter is equal to 1426 divided by 3 is equal to 475.33 mm square. So provide 12 mm dia bars, then spacing is equal to simple formula. We know that the simple formula is 1000 into by d square by 4 divided by AST. So we apply the D is equal to 12 mm because the 12 mm is our reinforcement diameter and AST is the 475.33. So final spacing is 237.93, so it is rounded as 240 mm. So provide 12 mm dia bars at 240 mm center to center distance. So as well as same as the find out the minimum distribution reinforcement or AST minimum. So minimum reinforcement we called as. So AST distribution is equal to, we get one constant formula, 0.12 percentage of cross section of the area. So 0.12 percentage means 0.12 divided by 100 into cross section means B into D. So B is equal to 3000 mm and D is equal to capital D. Overall depth for middle strip is 300 mm. So apply carefully here because the overall depth is 300 mm for middle strip. When you apply the column strip, you can overall depth is 200 mm. So check that. Okay. So for column strip we can take as a 300 mm. So per meter is equal to 1080 divided by 3 is equal to 360 mm square. So again for minimum reinforcement also finding on the spacing value. So provide 10 mm dia bars, spacing is equal to 1000 into by d square by 4. This is our formula. Then D is equal to 10 mm. We can assume that's a 10 mm. So apply that. Then AST is equal to take the minimum reinforcement value. 360 mm square is the minimum reinforcement value. So spacing is equal to 218 mm. So it will be taken as round off for 220 mm. So provide 10 mm dia bars at 220 mm center to center distance. The next for column strip positive moment. First we can find out the negative moment. Now we can find out the positive moment. So same formula. This formula also taken from our code book Vijam 96. So all the steps are the same. So only one value it will be changed in here because our column strip taken the max positive moment bending moment value. So in previous step for column strip taken as a negative moment value. So in this step we taken as a positive moment bending moment value. So positive bending moment is 58 kilonewton meter. So apply, there is here 58 into 10 power 6. So the same steps, so only change the constant values only. So apply the calculator, then take the least value for AST. So AST is equal to 604.32 mm square. So convert into per meter. So 604.32 divided by 3 is equal to 201.44 mm square. So next we find out the spacing for as well as same as the previous step for finding out the column strip negative moment steps. All the steps are repeating the same, but values will be changed only the AST values only. So spacing is equal to diameter is also 12 mm. We can assume that 12 mm. So AST only it will change. The AST it will be 201.44. So spacing is equal to 561.44. So 561 is more than 300 mm. So we can take in as the 300. 300 is the enough. The maximum spacing is equal to given as a 300. So no need to above the 300 mm because it will be such causes in failures, overload failures it will be there in that spacing. So maximum spacing with is a 300 mm you can provide. Then provide 12 mm dia bars at 300 mm center to center distance. So find distribution reinforcement. Same as the minimum reinforcement, we know that this is a constant formula 0.12 percentage into area of cross section. So 0.12 divided by 100 into 3000 into 300 mm. So A is equal to 1080 mm, the same answer. So for per meter is equal to 360 mm square. So provide 10 mm diabars, it will be same diabar. So spacing also same spacing. So assume as a 220 mm. So provide 10 mm diabars at 220 mm center to center distance. So for column strip, remaining negative and positive moment, because for our middle strip our negative and positive moment will be same, because that bending model will be same answers for 41 kilonewton meter. This is same for negative and positive moment. So you can find out only one reinforcement. It will take as a, when you apply in your field, split into the two types. So in our calculations you need to find out the only one, because the moment it will be same. So answer also will be same come from that. So same formula, then same steps. Then AST, take a least value for 687.24 mm square. Then again per meter convert to AST. So 687.24 divided by 3 is equal to 229.08 mm square. So provide 12 mm diabar spacing. So spacing is the same formula, only change the diameter values and AST values. It will be spacing the 493.70. So above 300 mm. So you will be taken as a 300 mm. So provide 12 mm diabars at 300 mm center to center distance for both positive and negative moments, because positive and negative moments moment values are same. So you can use as the same diameter and the same spacing will be taken for both positive and negative moments. The next find distribution reinforcements. So same formula 0.12 percentage of cross section area. Then convert into per meter. So per meter is 240 mm square. Then finding out the spacing. So spacing the same formula. Then provide 10 mm diabars. We can take as. Then apply this spacing also above to 300. So 327 will be there. So we can assume this 300 mm. So provide 10 mm diabars at 300 mm center to center distance for both positive and negative moments. So step number 7, check for deflection control. So PT is equal to 100 AST by BD. So this formula is taken in our code book IS 456 2000, page number 73. It will be there. One table column is top of that, values will be taken in our. So AST values only it will be changed. The remaining are the same. So in our deflection control, the deflection bit will be come in our middle strip portions only. The deflection not will come in the column strip or exterior designs. So especially maximum deflections it will be make provider middle strip portions only. So you need to apply the effective depth value based on middle strip value. So our middle strip effective depth is 170 mm. So apply that is. Then F is equal to 0.58 into Fy. This is our constant formula. This is page number 35 from IS 456 2000 code book. So F is equal to 4 is given. So take the modification factor is 1.8. Then finding out L by D max is equal to modification factor into 26. The 26 it will be taken from based on our supports. So it will be simply supported our continuous slab. So our flat slab it will be taken as a continuous slab, because more than 2 or more supports. So we can assume that this is a continuous slab. So continuous slab is taken as a 26. So this condition is in our code book page number 35. So modification factor is 1.8 and span bit depth ratio is 26 is equal to 46.8 is a L by D maximum. Then L by D provided is equal to span by depth ratio. The span length it will be known value for 6 meter. So it will convert into 6000 mm. So depth is equal to 170 mm. So L by D provided is equal to 35.2. So L by D maximum is greater than L by D provided. So hence safe. Thank you.